Hello and welcome to my Pre-Algebra review series. This video covers Chapter 1, Section 7, titled Inductive Reasoning. By the end of this video, you'll have reviewed the procedures for writing rules for patterns, making predictions, and counterexamples. Please leave a like if you find this video to be helpful. Give your classmates a heads up too. It will more than likely help them, and it certainly will help this channel to be seen by more students. If you would like me to cover any of these topics in greater detail, please leave a comment in the comment section below. I read them and do my best to answer each as time permits. Please subscribe to my channel and ring the bell icon to be notified every time I release a new video. Thank you. Let's get to it. Okay, before we get going, we're going to look at a couple definitions here. One is for inductive reasoning. Inductive reasoning is making conclusions based on patterns you observe. And conjecture is a conclusion that you reach by inductive reasoning is called a conjecture. Objective 1, reasoning inductively. Inductive reasoning is making conclusions based on patterns you observed. A conclusion you reach by inductive reasoning is called a conjecture. We'll be looking at these, a number of them here, as we move through this review period. Example 1, reasoning inductively. Visual patterns. Use inductive reasoning. Make a conjecture about the next figure in the pattern. Then draw the figure. So we have three boxes here, three squares, and with a square or a diamond inside. And these diamonds are making colored patterns in front of us here. And so what do we see? The first pattern we see is this one here, where we have this yellow pattern inside the boxes. So we look at that and we say, okay, this is obvious. We have this, it's whatever the pattern is, it doesn't make any difference. But we notice then that as we go to the next box, this seems to have moved up from the lower left to the upper left. So it moved from here up to here. And doing so, it looks like it seems to have rotated, is what it did, is it seems to have rotated to the clockwise. We look at the next pattern and we say it went originally from here over to here, and now it's over on this side. Again, the continued rotation in the clockwise direction. So inductively, you're going to think, well, if this was down here in the bottom left-hand corner, then it moved up to the upper left-hand corner, then it moved to the upper right-hand corner, the next place it's going to move to is to the lower right-hand corner. So you're going to think that it's probably going to move down here. Well, that's exactly what it is. The observation here is the colored triangle is rotating clockwise around the square. And the conjecture is that the next figure will have a shaded area in the bottom right corner. That's what we just drew right here, the bottom right. And that's what we drew this over here. And you see that's the next piece. That was your conjecture. Based on these three boxes up here on the top, based upon these three boxes right here, and what we saw happening, you conjectured that the next box is going to be looking like this one here, where the yellow triangle is in the bottom right corner. Example 1, check your understanding. The directions. Make a conjecture about the next figure in the pattern below. Then draw the figure. So what do you think is going to happen if we do this? The very first box, a circle here, has a triangle in it. That's pretty obvious. We know no more than it has a triangle. Then we go to the next box and we see, oh, it has a square in it. Well, we can start to see a relationship building here, because in the next box we have a pentagon. So we started off with 3 sides, then we moved to 4 sides, and then we ended up here with 5 sides, a 5-sided figure inside this circle. So what's our conjecture? What do we think the next one's going to be? Well, if I can draw it, let's see, it's going to be a 6-sided figure. You're going to have that, you're going to have this, you're going to have this, here, and you're going to have like that. 1, 2, 3, 4, 5, 6 inside the circle. Not a very good drawing, but that's exactly what it is. I'm going to draw a better one. How's that? Bigger, here, down here, and down here. And then the circle went around it. Not very good. Anyways, you get the picture. It went from pentagon to a hexagon. So now this one has 6 sides. That was your conjecture. It would have 6 sides. A 6-sided figure would be contained within this circle. Okay, example 2. Write rules for patterns. A. 30, 25, 20, 15 on continuously. What is the rule for what you see for this pattern? And I should mention that these only count for the future, right? You can't make a conjecture about or a rule with conjectures based upon what has already happened. So, like in this case, 30 is the starting number. We don't know if a number before that even existed. So you can only move into the future, right, when you're making conjectures. So 30, 25, 20, 15, what's the rule? Well, the rule here says that we start at 30 right here, start at 30, and subtract 5 repeatedly. Sounds pretty good. Next one would be what? 10 after this. 15, 10, 5, 0. Okay. B, write the rule for each pattern. What is this pattern? We have a 2, a -2, a 2, a -2. The next one's going to probably be a 2 and then a -2, right? So what is that rule? Alternate 2 and its opposite. So first you have 2, then you have its opposite. Then 2, here, 2, its opposite, 2, its opposite. And then we're going to have 2 and its opposite. Okay? For C here, 1, 3, 5, 12, 13. I said that wrong. 1, 3, 4, 12, and 13. So what's the rule? Okay, well, we start with 1. Okay, it says starts with 1. And then we alternate multiplying by 3 and then adding 1 is what we're saying here. So let's see. We multiply 1 times 3 is 3 plus 1 is 4. 4 times 3, right here, 4 times 3 is 12, plus 1 is 13. Okay. So if we did this again, if we're going to now multiply, we'd say 13 times 3 is 39, and plus 1, 40. It's going to be the next number. Okay, example 2. Check your understanding. Directions. Write a rule for each pattern. Well, let's start with A here. So what is our rule? Well, based on the previous slide and the way we got started with that, we're going to say, it looks like we're going to say the rule is that it starts with 4. Okay, good. Then what does it do next? If we start with a 4, 4 to 9, 9 to 14, it looks like if we go from 4 to 9, we're adding 5. So we're going to add 5. So 4 plus 5 is 9. 9 plus 5 is 14. 14 plus 5 is 19. Okay. 19 plus 5 is 24. 24. And 24 plus 5 is 29. Okay. B. What is the rule here? Well, again, we're going to say starts with, because we don't know anything else. We know it starts with 3. And we're going to do something to that number to get to the next number, it looks like, from what we can tell here. So it starts with 3. Then it does what? 3 to 9. Well, these look like they're multiplying. So we're going to do 3 to 9. Go multiply by 3. By 3. 3 times 9. 3 times 3 is 9. 9 times 3 is 27. Yep. 3 times 3 is 9. 27. 27 times 3 is 81. That is the rule. Let's check this one here. 1, 1, 2, 3, 5, 8. 1, 1, 2, 3. So here, if I say starts with 1, I can add 1 to get 1 because that's what looks like what the rule is here. But if I add 1, I get 2. If I'm at 2, I add 1, I get 3. But if I'm at 3, I add 1, I get 4. So that can't be the rule. There has to be some other. Well, another way to get this, to get the 1 here from this 1, I have to add a 1. But to get to the 2, I can add these 2 together. So if I start with 1, 1, 1, comma 1. Then I'm going to have 1, 1, and then I'm going to add, then I'm going to do what? Then, so I can't, we've already determined we can't just keep adding 1, but if I add these 2 together, I get a 2. So, and add previous, how's that? Add the previous number. Add the previous number. Because then I'll get these 2 numbers, I get a 2. I add these, that gets me the 2. So then when I add these 2 numbers, the 1 and the 2, I get a 3. And when I add these, the 1 and 2, I get a 3. When I add 2 and 3, I get 5. And when I add 5 and 3, I get 8. And so the next number is going to be 5 and 8 is 13. And then from 13 and 8 is going to be 21, right? Okay. There we are. I think those are the rules. Example 3, extending a pattern. So what we're going to do is we're going to take the pattern and we're going to come up with, it says write a rule for the pattern, blah, 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 which is 630, 320, 160, 80, and blah, blah, to find the next 2 numbers in the pattern. So we start off with 360, and then what? In order to get 320, it looks like we're going to take half of the value. Okay, so we're going to divide by 2, get 320. 320 divided by 2 is 160. 160 divided by 2 is 80. 80 divided by 2 is 40. And 40 divided by 2 is 20. Then, of course, the next number would be 10 and 5, and then 2.5, and on and on and on and on. Okay? Example 3, check your understanding. Write a rule for the pattern 1, 3, 5, 7, and find the next 2 numbers in the pattern. So it appears that we're doing, if we look here, it appears that we're doing 1, 3 plus 2, 2, 5 plus, it looks like we're doing 1 plus, we're starting with 1, start with 1, and then what do we get? We get 1, 3, 5, 7, 9, and 11. Okay? That should be our rule. Objective 2, predictions and counterexamples. Okay? With sufficient information, you can make a prediction based on reasonable conjectures. Such predictions will probably, but not necessarily, turn out to be accurate. So if you, based on good information, and you make a solid conjecture, you look at your information, you just think, well, this seems to make sense. If it does seem to make sense, and you can prove it to the pattern you're looking at, the chances are that you're probably, but not always, probably correct. Example 4, real-world problem solving. Statistics. See the chart below. Is a conjecture that the average hourly earnings in the year 2005 will be about $15.75. Is that reasonable? Well, looking at the chart, we can see that so this is for every 5 years, this chart's going. So if we go from here, 1980 to 1985, we went from 660 to 857. Well, that is from 7 to 857 is about $1.57 plus 60 cents. And it's around $2. So let's see where we go from there. For the next period, from 85 to 90, we go from $8.57 to $10. So that's from 9 to 10 is $1, and we're about $1.40. Okay. From 1990 to 1995, we went from 10 to 11.34, which is $1.50. From 95 to 2000, we went from $11.50 to 13 and a quarter or so. So now we're talking about $2.25, a little even more maybe. Okay, whatever. Let's see. Wait, $2 from 2000 to 2005 is $15.75. Is that a good conjecture? Well, the difference there is $2. It's $2. And if you recall, we've been doing about $1.50, whatever it is, right? Let's see what the words are going to say. The average hour earnings appear to increase from $1.50 to about $2.50 every 5 years. The conjecture of $15.75 in 2005 is reasonable, since it is about $2 more than the earnings from the year 2000. Yeah, it fits within the pattern. So we're making a conjecture based on the pattern we're seeing, that if I ask that question, you could say, yeah, it could very easily be $15.75. Not that it will exactly be, but it could easily be somewhere in there. We could be within $1.50 to $2.50. So, and $2 fits right into that pattern. Example 4, check your understanding. For the directions here, it says toss a coin 4 times and it comes up heads each time. So it's asking the question, is the conjecture the coin will come up heads on every coin toss reasonable? And then explain. Well, a coin has 2 sides to it, a heads and a tails. If it's a good solid coin and not a trick coin of some type, odds say that it should come up heads, at least half the time. It's one occurrence out of 2 possible, so it's 1/2 of the time. So is the conjecture that it'll come up every time reasonable? And the answer there has to be no, it's not reasonable. I'll even do that in red. It is not reasonable for it to come up. Why? What is? Well, if it's an honest coin, then the odds are 1 in 2. So it has to come up over the long haul 50% of the time. So it's going to come up, if it's an honest coin, it'll come up, it should or could come up heads. Oh, it's come up heads every time. It can come up tails the next time. It could come up tails the very next time you toss it. Example 5, analyzing conjectures. Inductive reasoning says, is each conjecture correct or incorrect? If it is incorrect, give a counterexample. So for A, every 4-sided figure is a rectangle. Is that true? Think about it. Well, we know a few that are, right? A box, a square is a rectangle. What else? Is a rectangle is a rectangle. Is there any other 4-sided figure? It says it's saying here, every 4-sided figure is a rectangle. Well, we know that that's not true, right? We could draw a parallelogram. We could draw something like this. It's not a rectangle, but it's a 4-sided figure. How about, well, it could be anything. It could be this, here like that, it could be like that. There's a 4-sided figure. Okay, so the answer is this is not a true conjecture. So it's no. Is this? No, it's not. And here's the counterexample. The absolute value of any number is positive. This is a bit of a tricky question. So I think you need to think about integers. And what are integers? So integers are all what? Are all counting numbers. So 1, 2, 3, 4, 5, right? So we can add 0 into this, and then we can add the negative numbers, -1, -2, -3. Those are our integers. But there's one of those that's neither positive nor negative. There's by rule. And that rule is that 0 is neither positive or negative. So the absolute value of any integer is positive. We're going to say no, just because of that rule right there, that 0 is not a negative or positive. The next one. The next figure in the pattern below will have 15 dots. Oh, 1, 3, 5, 10. And as we see, we're putting in rows of dots. We went from 1 to 2 to 3 dots to 4 dots. Yeah, the next one's going to have 1, 2, 3, 4, 5. It's going to have 15 because this is 10. 1, 3, 6, 10, 15. So that conjecture here is yes. It will have. Okay, example 5, check your understanding. Directions. Is each conjecture correct or incorrect? If it is incorrect, give a counterexample. The last digit of the product of 5 and a whole number. This obviously means 5 times some number. It doesn't matter what the number is. X, okay? So 5 times some number is either 0 or 5. Is that true? Well, yes, because you have 5 times 1 is 5, 5 times 2 is 10. That ended in a 0. 5 times 3 is 15. 5 times 4 is 20. So the answer here is yes. Yes. The number and its absolute value. A number and its absolute value are always opposites. Well, if you think about a number is 2, its absolute value of its opposite is -2, and 2 and -2, the absolute value, okay, these are the same, right? Same number. But if I were to choose 2 and the absolute value of 2, I get the same answer. So it's the number and its absolute value. The number and its absolute value. Well, here's the number. I picked 2. Well, they're not opposites. 2 and negative, the absolute value of 2 is not an opposite. There's no negative in here anywhere. So the answer here is no. And I think there's the example right here. It says, give an example. Here's an example. The next figure in the pattern has 25 dots. 1, 4, 9, 4 times 4 is 16. So what are we doing here? We're doing 1, then 2, a square with the side of 2, then a square with the sides of 3, a square with the sides of 4, and then one with 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And finally 1, 2, 3, 4, 5. So 4 by 4, here's 5 by 5. And 5 by 5 has 25 dots. So the answer is yes.